On the night of July 15th, 1977, an astronomer named Jerry Emin was helping to scan radio signals in search of signs of life from other planets. Suddenly, he captured a very strong and unusual signal that lasted 72 seconds, was much stronger than usual sounds, and seemed to come from the direction of the constellation Sagittarius. The signal appeared on the computer as a mixture of letters and numbers, 6EQJ5. When Jerry saw the next day, he was so surprised that he wrote, "Wow," next to on the printout, which is why people call it the wow signal. Experts believe that the signal was like a brief, flashing ray that only points towards us for a short time. We heard it when it was in front of us, but then it moved away, and we couldn't hear it anymore. Even after many years, nobody knows exactly where it came from or whether it was a message from aliens. Scientists assume that perhaps we only heard a small part of a longer signal. The telescope that found the wow signal was called Big Ear and was very large, as big as 3 soccer fields. It had a large mirror to capture signals from space and smaller mirrors to send them to the equipment that recorded them. But there was a problem with how Big Ear worked. After finding the wow signal, it took minutes to look at the same part of space again. By then, the signal was gone, which made it difficult to confirm its origin due to the size of Big Ear. It was difficult to track where the signals were coming from if the telescope could not remain focused on an area or quickly look back. Perhaps we would know more about the origin of the wow signal, or we would have captured more similar signals. Science suggests that the design of the telescope presented these challenges. After initially detecting the wow signal, there was a brief delay before the second receiver scanned the same point in the sky. By then, the signal had disappeared. This delay in detection has been a major obstacle to locating the signal. Source: the construction and operation of the Big Ear telescope show how the design of such devices can affect our ability to track and confirm extraterrestrial signals. If the telescope had the ability to continuously monitor a specific point in the sky, Big Ear shows how the design of these devices can affect our ability to track and confirm extraterrestrial signals. If the telescope had the ability to continuously monitor a specific point in the sky, we might have detected additional signals from the same area in the constellation Sagittarius. The Big Ear telescope was not like normal telescopes that use shiny mirrors to see light, but it was a radio telescope, which means that it used special metal frames to capture radio waves that we cannot see with our eyes. Unlike more modern telescopes, which can move in all directions to observe different parts of the sky, the Big Ear could only move its mirror slightly up and down. This meant that it could only observe a small part of the sky at a time. It was built this way because it was easier and cheaper than making a telescope that could move in all directions. To compensate, the people who built the Big Ear had a clever idea. They used the Earth's rotation to help move the telescope sideways, while tilting the mirror at different angles. The Big Ear could eventually look at any point in the sky. This clever use of the Earth's movement helped the telescope see more of the sky, even though it could not move much by itself. But there was a problem, since it depended on the Earth's rotation and could not remain focused on the same point in the sky for long. So if more signals arrived from the same area after the wow signal, the Big Ear could have missed them. Imagine that there were many signals, like an orchestra playing from that point in space, and the Big Ear only captured a small part of the music. That is why it was difficult to determine exactly where the wow signal came from. The challenges of searching for signals from outer space are mainly due to the fact that space is so vast. The search for signals from outer space is like casting a wide net in different places instead of waiting in one spot. Scientists use this approach because they cannot just observe one point in the sky for years hoping to capture a signal. This method increases the chances of capturing something, even briefly, even if it seems random. Searching for extraterrestrial signals is a careful process, unlike fishing, where fish can be attracted or scared away. Extraterrestrial signals do not change because of what we do. Scanning different parts of the sky with telescopes is the best strategy, given the enormous size of space and the uncertainty about the origin of a signal. However, this approach makes it difficult to follow up on unusual signals like the wow signal. Over time, telescopes have detected several mysterious and brief signals similar to the wow signal. These rapid bursts of radio waves are difficult to understand because we do not observe them long enough to obtain more information. Without continuous observation, many of these signals remain a mystery, and we miss important details about their possible origin. This leads us to an important point. Perhaps we have not found intelligent life from other planets because of how we search for it. It is just one idea among many. This discussion touches on some technical challenges in the search for extraterrestrial life, but there are also bigger and more speculative ideas about what life beyond Earth might be like. The question of whether there are aliens watching us is both exciting and complex, considering the large number of stars and galaxies, the right conditions for life, and that even intelligent life could be common outside of Earth. If only a few planets around these stars could harbor life, that would suggest that life could be widespread in the universe. There are several reasons why we might not have contacted other civilizations yet. One is the enormous distance between the stars, which makes communication or travel very difficult. Another is time. Civilizations could exist at different times and might never overlap. Another factor is how communication occurs. Advanced civilizations could use technology or methods that we do not understand or cannot detect. It is also possible that they choose not to contact us, perhaps to observe us as we study less developed species on Earth. When we look at the night sky, we see stars, planets, and galaxies scattered in the immensity of space, but everything we can see with our eyes, telescopes, and other instruments only represents a small fraction of the entire universe. It is estimated that the universe that we can observe is believed to be only 5%. The other 95% is something that we cannot observe directly. This 95% is something that we have not been able to discover. This hidden majority is composed of dark matter and dark energy, two mysterious components that play a crucial role in the structure of the universe. But why can't we see this 95%, and what does it mean for our understanding of the cosmos? To understand what we cannot see, let's first discuss what we can see. The observable universe includes all matter that emits, reflects, or interacts with light or other forms of electromagnetic radiation. This includes stars, planets, galaxies, nebulae, and even the cosmic background radiation, which is the residual glow from the Big Bang. When astronomers use telescopes to observe the universe, they depend on light to gather information. For example, when you look at the night sky, you're seeing light that has traveled through space for years, even millions of years, before reaching your eyes. This light carries information about the objects from which it comes, allowing scientists to study their composition, distance, movement, and much more. However, this visible matter that forms the stars, planets, and galaxies represents only a small portion of the total content of the universe. The other 95% of the universe is composed of two undetected components, dark matter and dark energy. Dark matter constitutes between 25% and 27% of the universe. We can only detect it through its gravitational effects on visible matter. Dark matter acts as a cosmic framework that guides the structure and shape of galaxies. The most difficult component to understand is dark energy, which constitutes approximately 68% of the universe. This mysterious force causes the universe to expand at an accelerating rate. Together, these components make up the fabric of the cosmos and influence everything from the smallest particles to the largest galactic structures. We still do not know exactly what dark matter and dark energy are, but we are quite sure that they exist. So what do we know? Unlike the matter with which we are familiar, dark matter does not emit, absorb, or reflect light, which makes it completely invisible to us. We cannot see it with telescopes or detect it using any of our traditional methods. So how do we know it exists? The existence of dark matter was first proposed when astronomers observed that galaxies rotated much faster than they should according to the amount of visible matter they contain according to the laws of physics. If a galaxy contains only the matter that we can see, its outer edges should rotate more slowly than its inner regions. However, observations show that the outer parts of galaxies moved as fast as the inner parts, suggesting that something else invisible was providing additional gravity. This invisible substance is what we now call dark matter. Although we cannot see dark matter directly, we can observe its effects on visible matter. For example, when light from distant galaxies passes through a region of space with a lot of dark matter, the light curves, a phenomenon known as gravitational lensing. This curvature effect allows astronomers to map the distribution of dark matter in the universe, even if they cannot see it directly. But what is dark matter made of? This is one of the biggest unanswered questions in modern physics. Some theories suggest that dark matter could be composed of particles that do not interact with light or other electromagnetic forces, so they remain invisible. These particles could interact only through gravity, so we can detect the gravitational effects of dark matter, but not the matter itself. Even more mysterious than dark matter is dark energy, which constitutes approximately 68% of the universe. Dark energy is believed to be responsible for the accelerated expansion of the universe. For most of the 20th century, scientists thought that the expansion of the universe, which began with the Big Bang, would gradually slow due to the gravitational force of all the matter in the universe. However, when astronomers observed distant supernovas, they discovered that these objects were farther away than expected, indicating that the expansion of the universe was accelerating. This unexpected acceleration led to the idea that some unknown force, now called dark energy, is driving the expansion. But what is dark energy? We don't know exactly what it is. Some theories suggest that dark energy could be a property of space itself, while others propose that it could be related to a new, unknown field or particle. Scientists are quite sure that they exist. Why? Because dark matter is essential for galaxies to form. When scientists studied the structure of the universe, they realized that the amount of visible matter is not enough to explain how galaxies are held together. The gravity of visible matter alone is not strong enough to form galaxies or complex systems without dark matter. The stars would probably be randomly scattered instead of grouped into the galaxies we see. This suggests that dark matter acts as the blueprint, keeping everything together. Although dark matter is invisible, it can be detected indirectly in areas with a lot of dark matter. Light passing nearby curves, creating a lens effect. This curvature of light reveals where dark matter is located, depending on its gravitational pull. So what is not dark matter? First, it is not ordinary matter without stars. Normal matter emits detectable particles, making it visible. If dark matter were only ordinary matter, we would have seen it already. Neither is it antimatter, since when antimatter contacts normal matter, it emits gamma rays. If dark matter were antimatter, we would detect these rays, but we do not. Dark matter is also not composed of black holes. Black holes are dense objects with a strong influence on their environment, while dark matter appears scattered throughout space. The gravitational effects of black holes differ from what we observe with dark matter. Scientists continue to test different ideas and conduct experiments to discover what dark matter really is. Even with precise tools, such as the European Space Agency's Planck spacecraft, we could detect less than 5% of the total observable universe. For years, scientists have been trying to solve the mystery of dark matter, but so far we only know it is there because of its gravitational effects on visible matter. British physicist Brian Cox suggests that dark matter could be composed of particles that we have not yet discovered. But how do we actually find dark matter? The search for this mysterious substance uses the world's largest physics experiment at the Large Hadron Collider in Switzerland. Instead of just trying to detect dark matter, they're trying to create it from scratch. They do this by colliding known particles at extremely high speeds, creating enormous amounts of energy. This energy could produce dark matter particles when protons collide. They usually create new particles, but most are light. Occasionally, these collisions create much heavier particles, and those are the ones scientists hope to find. Scientists believe they're getting closer to discovering what it is made of. One of the main candidates for dark matter are weakly interacting massive particles. These particles are believed to interact very weakly with normal matter, making them incredibly difficult to detect. Underground detectors are designed to capture these interactions and provide clues about dark matter. An interesting test comes from gravitational lensing. This occurs when light from distant objects, such as galaxies or quasars, occurs around a massive object, such as a cluster of galaxies, due to gravity. The amount of curvature tells us that there is dark matter that adds to the overall gravitational pull. Astronomers also play an important role in the search for dark matter, as they study the night sky and observe how galaxies and clusters of galaxies move. The way these large structures behave suggests that there is more mass than we can see, and that is where dark matter comes into play. For example, when astronomers observe the speed at which stars orbit around the center of galaxies, they realize that there must be additional invisible mass, probably dark matter, that holds everything together. Although we have not yet directly found dark matter, each experiment brings us closer to understanding this mysterious part of the universe. Dark energy is even more mysterious than dark matter. It is a type of energy that we cannot directly detect or measure, but see its effects, unlike dark matter, which clusters due to gravity. Dark energy is evenly distributed throughout space. In 1929, astronomer Edwin Hubble made a revolutionary discovery. He observed that light from distant galaxies shifts toward the red end of the spectrum as it travels through space. This effect, known as redshift, revealed something surprising. Hubble discovered that the farther away a galaxy is, the more its light shifts toward the red, while closer galaxies show less redshift. He said that this happens because the universe is expanding and, as light stretches, it shifts towards the red part of the spectrum, showing that space itself is getting bigger. Recent discoveries have taken Hubble's findings even further. Not only is the universe expanding, but it is also accelerating. Scientists used to think that gravity would eventually slow down this expansion or even reverse it. But now they know that dark energy is driving this rapid expansion, pushing the universe faster and faster. Space itself does not change as it expands, but new space is constantly being created everywhere. Galaxies are held together by gravity, so we do not feel this expansion in our daily lives, but we can see how it occurs throughout the universe. Wherever there is empty space, more is being created every second. So what exactly is dark energy? It appears to be a type of temporary energy in empty space that is stronger than anything else we know and continues to grow. Empty space contains more energy than everything else in the universe combined. This mysterious force. We still do not have a solid understanding of what dark energy is. We use the term dark energy to describe something we do not fully understand. It is one of the greatest enigmas of our universe, and its search could fundamentally alter our understanding of physics. Since the Big Bang, the universe has been continuously expanding, with space stretching and pushing galaxies further and further away. Initially, physicists thought that this expansion would slow down as the energy driving it ran out. However, a revolutionary discovery that won the Nobel Prize revealed the opposite. The expansion of the universe is accelerating. This led scientists to wonder what could be causing this unexpected acceleration. The mysterious force responsible was called dark energy, but giving it a name did not clarify what is really driving this process. Just like dark matter, which makes up about 25% of the universe and remains elusive, dark energy seems to defy the established laws of physics. Dark energy seems to increase as the universe expands, suggesting that something could emerge from nothing, which confounds our current scientific understanding. Several theories about the nature of dark energy have been proposed. It could be a new type of particle, an unusual form of energy, or an unknown force. However, no theory has fully explained this cosmic phenomenon. We know that dark energy accounts for about 70% of the universe and plays a key role in its formation and evolution. At the beginning of the 20th century, astronomers discovered the expansion of the universe and historically predicted that it would slow down due to gravitational forces. Contrary to these expectations, later findings indicated that expansion was accelerating, leading to the hypothesis that dark energy could be a property of space. According to Albert Einstein's theory of general relativity, space possesses its own energy, which increases as it expands. This inherent energy could be driving the accelerated expansion of the universe. Other perspectives suggest that dark energy could be related to a new type of field or particle yet to be discovered. Some scientists link it to the cosmological constant, a concept introduced and then abandoned by Einstein, acting as a uniform energy density filling space and driving the accelerated expansion of the universe. Alternatively, the phenomenon of dark energy could indicate that our current understanding of gravity is incomplete, which suggests that it might be necessary to revise our theories about how gravity works on a cosmic scale. Despite the numerous theories, dark energy remains a mystery. It emits neither light nor radiation, but does it interact with matter conventionally? Its existence is deduced from its impact on the expansion of the universe. As the universe expands, dark energy continues to separate galaxies at ever greater speeds. If dark energy persists in dominating the universe, it could expand indefinitely, becoming colder and more desolate as the galaxies move away from each other. Eventually, the stars would go out, leaving the galaxies as cold voids. Some speculation suggests that if dark energy intensifies, it could lead to the Big Rip, where its increasing force could eventually tear apart galaxies, stars, and even atoms. Despite the daunting nature of this mystery, the relentless pursuit by the global scientific community to understand dark energy gives us hope that we may soon discover more about this enigmatic force. The person who determines what dark energy really is could be considered the next Einstein. When we look around, everything we see and touch is made of matter. Small particles make up all the things we interact with, and over billions of years, these particles have come together to form stars and galaxies. They all follow the same physical laws and exist within the same space-time framework. But there was a time when the universe had nothing. So where did all this matter come from? Although it may seem that everything has to come from something, scientists also consider the possibility that everything came from nothing. But what does nothing really mean in science? To answer what was before the beginning of the universe, we first have to understand exactly how the universe was created from what seems like nothing. One of the main ideas of modern cosmology is the Big Bang Theory, which explains how our universe began and has evolved. Imagine all the stars, planets, and galaxies compressed into an incredibly hot and dense point. Scientists believe that this is how everything began some 138 billion years ago. Since that moment, the universe has been expanding and cooling. So, how we know that this happened? The Big Bang Theory is supported by numerous pieces of evidence. One of the key pieces is the cosmic microwave background radiation, which is like a residual glow from the early universe. This radiation gives us a picture of what the universe was like only 380,000 years after the Big Bang. Before that moment, the universe was too hot and dense for us to see anything. This radiation was accidentally discovered in 1965 by Arno Pennis and Robert Wilson. Another important discovery is the redshift of galaxies, which shows that galaxies are moving away from us, proving that the universe continues to expand. This was first observed by Edwin Hubble in the 1920s. The further away a galaxy is, the faster it seems to move away from us, supporting the idea that the universe was once much smaller, hotter, and denser. The Big Bang Theory also explains why the universe has certain amounts of light elements, such as hydrogen, helium, and lithium. These elements were formed in the first minutes after the Big Bang, when the universe cooled enough for protons and neutrons to combine and form nuclei. However, the Big Bang Theory also leaves us with big questions. For example, it does not explain what happened before the Big Bang or what is beyond the part of the universe that we can see. It also introduces the idea of cosmic inflation, a rapid expansion that occurred just after the Big Bang. This concept helps solve some problems of the theory and agrees with what we observe in the cosmic microwave background radiation. Before the discovery of cosmic microwave background radiation, there was a popular idea called the steady-state theory. This theory suggested that the universe had no beginning or end and that it remained the same in general, even as it expanded, constantly creating new matter. This theory was popular in the 1940s but lost support when scientists discovered cosmic background radiation in 1965, which strongly supports the Big Bang theory. Other ideas, such as the cyclic model, suggest that the universe goes through endless cycles of expansion and contraction. These theories are still being explored and developed, enhancing our understanding of how the universe began. After the Big Bang, the universe expanded and cooled. At first, it was a hot and dense soup of particles. As it expanded, it cooled, allowing the particles to come together to form the first atoms. These atoms formed the first stars and galaxies. The expansion of the universe continues today, with galaxies moving away from us in all directions. Let's think even further back. The first lasting particles, protons and neutrons, appeared about 1,000th of a second after the Big Bang. Before that, no material existed as we know it, but physics lets us go back even further in time to processes that took place before any stable matter existed. This idea of how the universe originated from nothing also leads us to the concept of the Great Unified Epoch. A probable idea is that the universe was full of a mixture of particles, including quarks, which are the basic components of protons and neutrons. There was an almost equal amount of matter and antimatter. Each type of matter particle, like a quark, has an antimatter counterpart that is almost identical, but with a key difference. When matter and antimatter meet, they destroy each other in an explosion of energy, which means that these particles are constantly created and destroyed. But where did these particles come from in the first place? If we think in terms of quantum field theory, this tells us that even the vacuum, which we consider empty space, is full of activity in the form of energy fluctuations. These fluctuations can cause particles to appear and disappear shortly thereafter. This may sound strange, but these particles have been observed in many experiments. The vacuum of space is full of particles that are constantly created and destroyed, apparently out of nowhere. However, this suggests that the quantum vacuum is actually something more than nothing. Now, let's ask ourselves, where did space-time itself come from? To answer this, we have to go back to the beginning, to the Planck era. This period was so early in the history of the universe that our best theories of physics no longer work. It occurred only a tiny fraction of a second after the Big Bang. During this time, space and time were affected by quantum fluctuations. Usually physicists use quantum mechanics to understand tiny particles and general relativity for large cosmic scales, but to understand the Planck era, we need a complete theory of quantum gravity that combines both. We still don't have a perfect theory of quantum gravity, but ideas like string theory and loop quantum gravity suggest that ordinary space and time come from deeper microscopic processes. What we experience as space and time results from quantum processes. At this moment, they don't make much sense to us because we are used to the large-scale world. Quantum fluctuations occur constantly, even in what we consider empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can arise from the vacuum, exist for a brief instant, and then destroy each other. This phenomenon is known as quantum foam, but quantum fluctuations alone do not explain the large scale and complexity of the universe. There is also dark energy, a mysterious force that fills all space and accelerates the expansion of the universe. Although we do not fully understand dark energy, it is believed to play a crucial role in the creation and evolution of the cosmos. So how did we go from quantum fluctuations and dark energy to the vast structured universe we see today? The answer lies in inflation, a rapid expansion that occurred fractions of a second after the Big Bang. During this brief period, the universe expanded at an incredible rate in the Planck era, setting the stage for the formation of galaxies, stars, and planets. Our usual understanding of space, time, and cause and effect falls apart despite this. All candidate theories of quantum gravity describe something physical that occurs during the Planck era as some quantum precursor of ordinary space and time. But where did that come from? Even if causality doesn't work in the usual way, it could still be possible to explain parts of the universe of the Planck epoch in terms of other parts. Unfortunately, our best physics still cannot provide clear answers. Until we develop a theory that explains everything, we will not be able to give a definitive answer. The most we can safely say is that physics has not yet found any confirmed case of something coming from nothing. Now that we understand the beginning of the universe, we will begin to explore what was before nothing. None of the evidence of cosmic background radiation, quantum fluctuations, or the Big Bang. The Big Bang theory explains that the universe began from an incredibly dense and hot point called a singularity. Think of a singularity as a point where everything we know about space and time disintegrates. This singularity raises some important questions. If our usual laws of physics applied here, what would be the rules for understanding this? We have to look at the ideas of Albert Einstein. His theory of relativity changed our way of seeing the universe by connecting mass and space-time. According to his theory, time is not fixed, but changes depending on the gravitational attraction of massive objects. He showed that massive objects like Earth slow down time. Now, if mathematics slows down time, imagine what the singularity, which contains all the mass of the universe, would do. It would stop time completely. Therefore, according to Einstein, the idea of what was before the Big Bang does not make much sense, since time itself did not exist. Cosmic microwave background radiation is a key test, as it comes from an era approximately 380,000 years after the Big Bang, when the universe was cooling and forming hydrogen atoms. Before this 380,000-year mark, the universe went through several stages, starting from the Planck era to the Great Inflationary Unification, the Electroweak, and the Hadron Epoch. In each stage, different particles and forces were seen that evolved into what we know today when we talk about the universe at such a small scale that quantum mechanics replaces classical physics. This led scientists like Stephen Hawking to think about how quantum theory could be applied to the entire universe. Here is where inflationary quantum cosmology comes into play. Unlike classical theories that describe the singularity as a point with zero volume, quantum cosmology suggests an element of uncertainty, meaning that we cannot determine the exact moment when the universe was created and that particles can appear and disappear from what we call a vacuum. In physics, a vacuum is not completely empty, but rather a state devoid of particles. According to the Heisenberg uncertainty principle, there is always some fluctuation, so a perfect vacuum with zero field values is impossible. This may sound strange, but Einstein's famous equation E equals mc squared helps explain it. The positive energy of stars and galaxies must be balanced by an equal amount of negative energy, such as gravity. If the total energy of the universe is zero, then it is possible that it comes from nothing. The idea that hundreds of billions of galaxies can emerge from nothing seems incredible. However, the Einstein equation E equals mc squared gives us some clues. According to this equation, all the positive energy of stars, galaxies, and other celestial bodies must be balanced by an equal amount of negative energy, which manifests as gravity in a closed universe or one that will eventually collapse on itself. These positive and negative energies would cancel each other perfectly, resulting in a net energy of zero for the universe as a whole. Stephen Hawking wondered how a universe with zero total energy could emerge from nothing. He suggested that the negative energy of gravity could balance the positive energy needed to create matter. This makes empty space stable. The physicist Alexander Vilenkin expanded on this idea by demonstrating that a small vacuum full of energy could spontaneously appear from nothing and expand to become the universe we see today. This means that our universe could have started from a state of nothing, where time did not exist. So what was there before the Big Bang? The theories that we have explored suggest that time itself began with the Big Bang, which makes the idea of before quite complicated, from singularities to quantum fluctuations. These ideas show how incredible and mysterious our universe really is. The Big Bang theory explains how the universe expanded from an extremely hot and dense state, but it does not tell us what happened before that moment. According to the theory, time, space, matter, and energy began with the Big Bang. However, some scientists have ideas about what may have existed before the Big Bang. An interesting idea is the Big Bounce. This theory suggests that the universe goes through cycles of expansion and contraction. Another intriguing idea is the concept of a multiverse. This theory proposes that our universe is only one of many, each with its own set of physical laws. In this model, what existed before our Big Bang could have been another, completely different universe. These ideas expand the limits of our current knowledge and explore speculative possibilities. They are based on advanced concepts of quantum physics and the still-developing field of quantum gravity. Scientists are working to connect the dots between quantum mechanics and general relativity to better understand these possibilities. Although these theories offer exciting visions of what might have existed before the Big Bang, they remain largely theoretical, highlighting the profound mystery of the origins of our universe. By looking back in time, we can explore the origins of each cosmic structure. Each discovery leads to another question. Where did this come from? And how was it formed? These questions continue. We live in a world with 3 dimensions: up and down, left and right, and forward and backward. These are the directions in which we can move. Time is another dimension that we experience as we move from the past to the future. Together, these constitute what in physics we call space-time. Dimensions are like different directions you can move in, similar to the lines on a graph. We usually only perceive 3 dimensions, but what if there are more dimensions that we cannot see? Theories like string theory and M theory suggest that there could be additional dimensions. According to string theory, the smallest parts of our universe are not tiny points, but tiny vibrating loops of energy called strings. The mathematics behind string theories suggest that 10 or 11 dimensions must exist for everything to work properly. String theory attempts to explain all natural forces, such as gravity, electromagnetism, and forces within atoms, by proposing that everything is made of these strings. The way these strings vibrate determines the type of particles they become. So why can't we see these additional dimensions? They could be incredibly small and tightly folded, making them impossible to detect with our current tools. For example, imagine an ant walking on a tightrope. For the ant, the rope looks like a line because it cannot perceive its width. Similarly, these additional dimensions could exist, but be too small or hidden for us to perceive. If these higher dimensions are real, they could help us answer some big questions in physics, such as why gravity is much weaker than other forces. Perhaps gravity extends into these additional dimensions, making it appear weaker in our 3-dimensional world. These higher dimensions could help us better understand particles and forces. They could connect all the different forces into a single complete picture, leading to new technologies and a deeper understanding of the universe. Scientists are looking for evidence of these higher dimensions. One way is to study how gravity behaves at very small scales. If higher dimensions exist, they could cause slight differences in gravity that we can observe in laboratory experiments. Another method involves high-energy particle collisions, such as those of the Large Hadron Collider. In these experiments, particles collide at very high speeds. If any particle disappears into higher dimensions, it could be a clue that these exist. There are also other interesting ideas about higher dimensions. For example, some theories suggest that our universe could be a 3-dimensional brain floating in space with more dimensions. In this idea of a cerebral world, our universe could be just one of many parallel universes, each existing as a separate brain in space with additional dimensions. This idea opens possibilities about how these universes could interact, for example, through gravity or the exchange of particles. Another idea related to higher dimensions is the multiverse theory. This theory suggests that our universe is just a bubble in a vast space full of other universes, each existing in a higher dimension. These different universes could have their own physical rules and even interact with each other. For example, if these universes collided, it could produce a massive explosion similar to the Big Bang that created our universe. Although the concept of higher dimensions is fascinating, it is still just a theory. One of the biggest challenges is that these dimensions are not something we can directly see or measure today. To detect them, we would need extremely high energy or very precise measurements beyond what we can do with current technology. Mathematics is crucial to help us explore the concept of higher dimensions. Many of the theories that suggest the existence of these additional dimensions are based on complex mathematics from areas like geometry, topology, and algebra. These areas of mathematics help us imagine and understand spaces that go beyond the three dimensions in which we usually think. Mathematicians and physicists work together to create models that predict how these higher dimensions could affect what we observe in the universe. Then they test these models with experiments and observations. Quantum mechanics, which studies how particles behave at very small scales, could also be affected by higher dimensions. The strange behaviors we see in quantum mechanics could be due to interactions that occur in spaces with more than three dimensions. So, do higher dimensions really exist in the universe? Although we do not yet have concrete evidence, the possibility that higher dimensions exist is an exciting area of research in theoretical physics. If these dimensions are real, they could change our vision of the universe and reveal new knowledge about the nature of reality. We are guaranteed to find an identical copy of our entire universe, as well as countless multiple universes, which raises the question, are there other versions of you in parallel universes? Variations of reality, where things are similar to what we know but different, are now considered a real possibility. It probably doesn't surprise you that studying parallel universes was once considered crazy in the scientific community. It even alienated the people who decided to dedicate themselves to it. But now theoretical physicists have realized that parallel universes are possible, at least mathematically. One of the reasons comes from the strange world of quantum physics. The most important thing to remember about quantum mechanics is that it is really strange. It is the study of subatomic particles, which are the basic components of everything in the universe. Quantum mechanics tells us that these particles can behave as both particles and waves at the same time. This dual nature divides our reality, creating multiple different universes. The idea is that when you measure a particle that exists in two places at the same time and find it in one place, there's another version of you in a different world that finds it in the other. Both worlds are equally real, so the quantum multiverse is not separated from us by distance. It is not a distant place. It is effectively right here in space, but the complexity of quantum dynamics prevents these different branches from interacting. Whether you like it or not, the idea that we live in a multiverse is now the prevailing scientific view. Another theory is based on mathematical inevitability. If our universe is made of a finite amount of simple matter, then it follows that other universes are made in a similar way. Just as a house is built from basic blocks such as bricks, everything in our world is made of elementary particles. If a random process organizes these particles in space, there are countless ways this could happen. If this process is repeated in an infinite number of other spaces, we are destined to find an identical copy of our universe, as well as countless variations in which things are similar but slightly different. There could even be a version of me out there that is identical in every way, including the feeling that he is me. Another theory, called inflation, explains how the universe expanded rapidly in the first fraction of a second after the Big Bang. This rapid expansion created bubbles or pockets of time and space where other universes could form. If this theory is correct, then these pocket universes could have their own laws of physics, which means that there could be another you in those universes who can walk through walls or fly through space. According to quantum theory, a new version of you and a completely new universe are created with every decision you make. For example, every time you flip a coin and say heads or tails, the universe splits into two worlds depending on the outcome. Our experience of this is like walking through a garden with branching paths. When we get to a fork, we choose one path or another, heads or tails, but both paths exist at the same time. We only experience one of them. There are countless universes out there, and ours is just one of them. Then there is the mosaic model, which suggests that an almost identical copy of our universe exists somewhere else, in this type of parallel universe. There's another very similar one, but with small differences. We are destined to find infinite variations in which things are like here, but still different. For example, in one universe, the asteroid that wiped out the dinosaurs did not impact Earth, so there are no humans, only dinosaurs walking through Winchester today. In another, I did not become a physicist, but enjoyed life as a waiter. Then there are many more in which the only difference is something small, like the way I decided to dress. All these ideas suggest that there are many strange and wonderful universes out there. Although we cannot see the entirety of our own universe, scientists believe they may be getting closer to understanding these possibilities. The truth usually goes through 3 stages. First, it is ridiculed, then strongly rejected, and finally it becomes evident. Perhaps we are now reaching that stage of evidence. A mysterious characteristic within the cosmic microwave background is the cold spot, a large area with lower temperatures than average. An interesting theory about the cold spot is that it could be a cosmic bruise left when our universe collided with another. This idea supports the concept of the multiverse, in which multiple universes exist and sometimes interact. In 2007, scientist Laura Mersini-Houghton discovered something unusual. She found evidence that our universe had collided with another. Scientist Laura Mersini-Houghton discovered something unusual. She found evidence that appeared to show 2 universes crossing. The detection of a cold spot was one of the signs she predicted when tracking the quantum entanglement of our universe with other surviving universes. She suggested that this cold spot may have slowed expansion in that part of our universe, which would have resulted in the colder temperatures we see today. Recently, there has been a major breakthrough in the theory of inflation, which predicted that if the universe expanded rapidly, it would send waves through space. These waves are known as gravitational waves. We had not detected anything like it until 2015, when 2 experiments called LIGO and Virgo managed to detect gravitational waves coming from the fusion of 2 black holes. This detection makes it more likely that we can detect gravitational waves from inflation. But why should we care if multiple universes exist? Well, it is related to the question of what our universe is expanding into. If other universes exist, perhaps ours expands while the neighbors contract. This could give us more information about our own universe, especially about how it might end. Over time, our universe could expand until other neighboring universes had their own Big Bang and began to expand towards us, causing our universe to contract and possibly end in a big crunch instead of a Big Bang. Over time, these ideas have led to investigations into similar anomalies that might resemble them. According to the theory of cosmic inflation, everything in the universe should be evenly distributed across the sky, but anomalies such as the cold spot of the cosmic microwave background challenge this idea, hinting that the history of our universe may be more complex than we thought. British physicist Brian Cox has discussed how the idea of multiple universes fits into a concept called eternal inflation. According to this theory, our universe is just a bubble in a vast space-time filled with other bubbles. These bubble universes are constantly forming. The process begins when a certain region of space stops expanding rapidly. However, not all regions of space stop expanding at the same time. Some areas continue to expand, leading to the continuous creation of new universes. Each of these universes may have its own unique physical laws, which could be very different. When we think about how vast the universe is, it is natural to wonder if we really matter, if we are special, or if there are other life forms out there in the cosmos. This leads us to the question of whether the universe was created specifically with us in mind. This idea is related to the anthropic principle, which suggests that the basic laws of the universe appear to be perfectly designed to sustain life, especially intelligent life, such as that of human beings. The exact strength of gravity, electromagnetic forces, and the functioning of atoms are crucial for life. Even small changes in these constants could make life as we know it impossible. So, does the fact that the universe is so precisely tuned mean that it was designed just for us? Some scientists think that the conditions that allow life are too perfect to be a coincidence, suggesting that there could be a purpose behind it. On the other hand, Others believe that this very precise adjustment is only the result of natural processes and random changes. They argue that in a universe as vast as ours, it is not surprising that at least one planet like Earth has ended up with the right conditions for life. The multiverse theory offers another perspective. It suggests that our universe could be just one of many, each with its own set of physical laws and constants. In this multiverse, only a few universes might have the right conditions for life. If this theory is true, our universe is not particularly unique. It is just one of the few where there could be life, which makes the idea of fine-tuning less surprising. The search for life beyond Earth also plays a role in this discussion. Finding life elsewhere, whether microbes on Mars, in the oceans of moons like Europa and Enceladus, or on distant exoplanets, would suggest that life is not unique to Earth, that it could exist anywhere conditions are right. Such discoveries could change the way we think about the rarity of life in the universe. Beyond science, philosophical views also influence how we understand the universe. Some people find comfort in believing that the universe has a specific purpose, while others see beauty in its randomness and infinite possibilities. Regardless of whether the universe has a purpose or not, our natural curiosity and our desire to explore are key human characteristics. To ask ourselves these big questions not only drives scientific progress, but also helps us to better understand the cosmos. Science shows us a vast and seemingly indifferent universe, which can make us feel small, but some argue that we could still have a special place in the cosmos because the laws of physics are so perfectly tuned to make life possible. For example, the exact strength of the electromagnetic force is crucial for stars to produce carbon, essential for life. Even the energy in empty space seems adjusted so that intelligent life arises. This idea of fine-tuning has given rise to various interpretations of the anthropic principle. One opinion suggests that the universe was designed on purpose with us in mind, possibly by a superior intelligence. Another idea, known as the principle of life, proposes that life is a natural part of composition. However, these ideas are not widely accepted by the scientific community. Another way to view the anthropic principle is to say that the universe exists because we are here to observe it. A more practical view is that the universe seems perfectly suitable for us simply because we live in a life-sustaining part of it. This could be due to the possibility that multiple universes exist, each with its own set of physical laws, ours being one of the few that can house it. Music. Look closely at this photo. This is Eugene Cernan, the last astronaut of the Apollo program to step on the moon, but something does not fit in the image. Do you realize? The night sky looks completely empty, without any stars. In fact, all the photos taken during the Apollo missions show a sky without stars, even though the universe is full of trillions of stars. The Apollo astronauts said they could not see a single star from the moon. This lack of stars has fueled conspiracy theories, with some people claiming that the moon landing was false. But the real explanation is much more interesting and goes beyond any conspiracy theory. The reason why the stars do not appear in the photos taken on the moon is mainly due to the camera's settings. When astronauts take photos on the moon, they usually capture the lunar surface, which is very bright. The surface of the moon is illuminated by the sun, and to correctly capture this brightness, the camera uses a fast shutter speed and a low ISO setting. However, when we look at the night sky from Earth, what we mainly see is darkness. Why does space seem so empty? This problem was first raised by the German astronomer Johannes Kepler in 1610. Our galaxy, the Milky Way, is huge, with between 100 and 400 billion stars. In addition, the observable universe has trillions of galaxies, each with trillions of stars. A thorough study suggests that the sky should be as bright as the surface of the sun, but when we look up at night, what we mainly see is darkness. This mystery, known as Olbers' paradox, took almost 300 years to resolve. With so many stars in all directions, astronomers wondered why the whole sky is not bright and full of light. Olbers' paradox is based on the steady-state theory. Imagine a universe in which everything has always remained the same and always will. The position of the stars, the galaxies, everything. This was the main idea behind the steady-state theory, which used to be the most popular explanation of a universe. It said that the universe was infinite, without beginning or end, uniform in all directions, and that it was not expanding. With this theory in mind, astronomers were faced with a big question. If the universe is full of stars and has always existed, why is the night sky dark? According to the steady-state theory, even the most distant stars should have reached us already, filling the sky with their glow. One of the first ideas was that perhaps the stars are too far away to affect our night sky, but this did not make sense with the steady-state model. If the universe is infinitely old, there's been enough time for the light from any star to reach Earth, even from the farthest parts of the universe, and this light should fill the sky without leaving dark areas. Johannes Kepler had a different idea to solve the paradox, which went against the steady-state theory. He suggested that the universe is not infinite, but that the stars only extend to a certain limit and beyond there is only empty space. This idea was interesting, but raised new questions. How far does this space with stars go, and what is beyond that edge? Kepler's idea, the limited universe, had its own problems. If the universe had a limit, the combined gravity of all the stars and planets could attract everything back towards the center, causing the universe to collapse. Due to these challenges, most astronomers continued to believe that the universe was infinite, which meant that the paradox and the steady-state theory remained unresolved for almost 200 years. Then, a famous German astronomer named Heinrich Olbers again called attention to this old question. Why is the night sky dark and seems empty? Since then, Olbers' name has become closely linked to the paradox. At that time, people still believed that the universe was immutable. Olbers suggested a simple idea. If the universe is infinite, it would be full of dust and rocks. These particles could block the light from distant stars, making them appear dimmer to us. This cosmic dust and rocks would absorb and block the light from the stars as they move through space. Today, many people still think of space as Olbers did, similarly to how clouds block sunlight and hide the sky. Just like clouds, cosmic dust and rocks can obscure the light from the stars. But Olbers' explanation was not the whole story. Over time, the dust and rocks that block the light would heat up and start to glow themselves, which means that the universe would still be full of light, just like before. The dust and rocks would only temporarily block the light before releasing it again. So the total amount of light that reaches us would still be the same. So, what really solves this mystery? It took another 100 years to find a real answer. In 1929, Edwin Hubble used his powerful telescope in the hope of finding evidence that the universe was shrinking, which would support the idea of a limited universe, as Kepler suggested. However, Hubble discovered that the galaxies were moving away from us, and that the further a galaxy was, the faster it seemed to move away. This showed that the universe was not staying the same or collapsing, but actually expanding. This discovery led to a new question. What does an expanding universe mean for its origin? Scientists now believe the universe began as something incredibly small and dense, then expanded rapidly in a process called cosmic inflation. As the universe expanded, it cooled, eventually allowing stars and galaxies to form. This understanding led to what we now call the Big Bang Theory. Scientists believe that all this began about 138 billion years ago and is currently our best explanation of how the universe began. Today, most scientists agree that the universe is about 138 billion years old. When we observe light that is 138 billion years old, we do not see stars, not because the light has not reached us, but because we're looking back to a time when stars did not even exist. The more we look into space, the further back in time we see, until we reach what looks like the edge of the universe. This is not a real edge, but the oldest light we can see, known as cosmic microwave background, is the glow left over from the Big Bang. When we use telescopes to look beyond the first stars, we see this special type of light. It is not light from the stars, but light left over from the Big Bang. It forms a background sky, beyond where the stars are. However, the Big Bang Theory raises a new question. It suggests that the universe used to be much brighter, especially during a time called the recombination era. Back then, the entire sky would have been as bright as the sun because the universe was very hot. This means that the background psi of the Big Bang, known as cosmic microwave background radiation, should have been very bright according to the Olby paradox. This bright background should make it difficult for us to see any faint stars in the night sky. Since the Big Bang occurred 138 billion years ago, the universe has followed three main rules as it grows and changes. At first, the universe was incredibly small, very dense, and extremely hot. Second, only a fraction of a second after its start, the universe began to expand and cool. And this is really important. The universe will continue to expand and cool. Astronomers believe that this will continue until the universe cools so much that all the heat disappears, a scenario they call the thermal death of the universe, also known as the Great Freeze. In this future scenario, the universe will have expanded so much that it will cool completely and all thermal energy will disappear. These rules show us that our universe has been getting bigger for the last 138 billion years. When the universe began, it was full of very bright and hot light. As the universe expanded, this light stretched, becoming the wavelengths, making it colder and dimmer. This stretching of light is known as the redshift effect. It is the reason why cosmic background radiation is not extremely bright. Thanks to the discovery of redshift and cosmic background radiation, we now know that the Big Bang and the expanding universe solve Euler's paradox. The universe began from a single point and expanded rapidly during the Big Bang. Over billions of years it has cooled because the universe is not infinitely old. There's a limit to how far we can see into space. The effect of redshift also makes the light from distant objects appear dimmer. These factors together explain why the night sky looks dark today. The darkness of the night sky shows us that the universe is always changing and growing. Seeing a dark sky instead of a bright one tells us that the universe began with the Big Bang and has been expanding ever since. The night sky is a quiet reminder of how the universe began as a very hot and dense place. This understanding not only solves Euler's paradox, but also helps us appreciate how incredible and complex the universe really is. Music. The moon is one of the largest objects in our solar system, almost as large as Mercury. This size raises an interesting question. How did Earth and the moon get to be like this? Why do these two bodies orbit each other? There are some interesting facts about the Earth and the moon. For example, this image taken by a space probe in orbit around Mars shows the Earth and the moon from the perspective of Mars. One of the surprising facts about the moon is that it has very little iron in its core, unlike the Earth, which has a lot of iron in its core, responsible for its magnetic field. This difference raises questions. If the moon formed near the Earth, why does the Earth have so much iron, or the moon have so little? Another curious aspect is the amount of spin in the Earth-Moon system. The moon is quite large compared to the Earth, orbits quickly, and both the Earth and the moon rotate. In physics, the principle of angular momentum tells us that spin does not appear out of nowhere. It has to come from somewhere, so when we see the Earth and the moon spinning rapidly with the moon orbiting rapidly around the Earth, there must be an explanation for that. Where does all this angular momentum come from? One of humanity's greatest achievements was landing on the moon in 1969. During this mission, we collected lunar rocks and brought them back to Earth. These rocks turned out to be very similar to the rocks found on Earth, suggesting that the moon and Earth may come from the same source. By studying the decay of radioactive elements in lunar rocks, we can determine their age. These rocks appear to be between 30 and 50 million years younger than the Earth. Although this difference may not seem huge, given that the Earth is about 45 billion years old, it suggests that the moon formed a little later than the Earth. Another point refers to isotopes, which are different versions of the same element. For example, carbon-12 has 6 protons and 6 neutrons, while carbon-14 has 6 protons and 8 neutrons. The same concept applies to oxygen, too. The proportion of different isotopes of oxygen can be measured very precisely, and these proportions differ throughout the solar system depending on the distance at which a planet formed from the Sun. However, on Earth and the Moon, these proportions are very similar, which points to a common origin. So a question arises. The Moon is younger than the Earth, rotates rapidly, is composed of similar materials, but lacks iron. What explains this, then? There is a widely accepted theory that explains all these things, though some people question it, which is natural in science. This theory makes sense given the evidence. Scientists have several ideas about how the Earth and the Moon formed, but one of the most accepted is the giant impact hypothesis. The giant impact hypothesis suggests that about 50 million years after the Earth formed, another planet approximately the size of Mars came very close to the Earth and collided with it in an oblique blow, releasing much without hitting the Earth's core. When planets form, heavy elements like iron sink to the center. So, when this collision occurred, the material torn off had little iron, since most of the Earth's iron was already concentrated in its core. This collision also caused a lot of spin, similar to how a soccer ball curves when kicked sideways, which explains why the Earth-Moon system has so much angular momentum. The Moon formed from the debris of this impact, so it has materials and isotopes similar to those of the Earth, since the collision occurred 50 million years after the Earth's formation. This also explains why the rocks on the Moon are slightly younger than those on Earth's. The Moon likely formed from a planetary collision around 45 billion years ago. All the evidence supports this idea, based on 4 key observations about the Earth and Moon. In addition, samples collected from the Moon during the Apollo missions have been analyzed in laboratories, which further supports this theory. Interestingly, this collision not only created the Moon, but also played a key role in shaping the future of the Earth. The impact probably tilted the Earth's axis, giving us seasons. Without this tilt, our planet might not have the weather patterns that support such diverse life. The Moon also helps stabilize the Earth's axis, which prevents extreme changes in its inclination over time, which would have major effects on our environment. The gravitational interaction between the Earth and the Moon creates the tides, which have influenced the evolution of life on Earth greatly. The regular rise and fall of ocean levels has shaped coastal ecosystems and human activities for millennia. Another fascinating fact is that the Moon is slowly drifting away from the Earth. Measurements show that the Moon moves about 38 centimeters away from the Earth every year. This slow separation affects the Earth's rotation and the length of our days. Millions of years ago, the days were shorter, and as the Moon continues to recede, the days on Earth will gradually lengthen. While the giant impact hypothesis is the most widely accepted theory, there are other interesting ideas as well. One of them is the fission theory, which suggests that the Moon was once part of the Earth, but separated due to the rapid rotation of the planet in its early history. This rapid spin caused a piece of terrestrial material to break off and eventually form the Moon itself. However, this theory has difficulties explaining the current orbit of the Moon and the physics behind such separation. Another theory is the capture theory, which suggests that the Moon formed elsewhere in the solar system and was subsequently captured by Earth gravity. This could explain why the Moon has a slightly different composition than the Earth. However, capturing such a large body without it breaking apart or escaping seems very unlikely. Despite these theories, the exact process of the Moon's formation remains a topic of ongoing scientific research and debate. The unique relationship between the Earth and the Moon has greatly impacted life here. The Moon's gravitational attraction creates the tides, which have influenced the development of ecosystems and human civilizations for millennia. The rise and fall of sea level has affected life along the coasts greatly. The Earth-Moon system remains a fascinating area of study, offering insights into the formation and evolution of planetary bodies. The differences in composition, shared angular momentum, and ongoing interaction between the Earth and its natural satellite reveal a complex and evolving story about our place in the cosmos. This photo, taken by a telescope in 1917, shows a blurry spot with dark marks. Back then, even respected astronomers thought these marks might be signs of vegetation there. However, this idea was disproven when spacecraft began visiting Mars. The first was Mariner in 1965, which sent grainy images of the planet's surface. After seeing these images, President Lyndon Johnson commented that life, as we know it, might be more unique than previously thought. Since then, many spacecraft have visited Mars. Today we know Mars as a planet with geological giants, such as the Valles Marineris, a canyon that stretches for almost half the planet. The Grand Canyon of the Earth could fit into one of its side channels. Mars is also home to huge volcanoes and shows evidence of ancient lakes and possibly even oceans. The Curiosity rover is currently exploring a dry lake and has found indications of organic molecules and minerals that form in standing water. We now understand that Mars was similar to Earth about 3,000 to 3,500 million years ago, with rivers, oceans, and seas. It could have been an inhabited world, but we still don't know if life ever arose there at all. This changes our view of Mars. A planet with water has everything needed to build a civilization and sustain life. Even if there were no Martians billions of years ago, and even if there are no Martian microbes today, there could be Martians in the future, because those Martians will be us. Mars, often called the Red Planet, has long fascinated us with its mysterious landscapes and the possibility of life beyond our Earth. One of the biggest questions is what happened to its water. Evidence suggests that billions of years ago, Mars had large amounts of liquid water that flowed through rivers and possibly into large oceans. Today, however, it is a cold, dry desert with only traces of water in its atmosphere and at the polar caps. So what caused this change? To understand what happened to Mars' water, we have to look back to its early history. Features such as river valleys, lake beds, and mineral deposits show that Mars once had a much denser atmosphere that allowed liquid water to exist on its surface. This atmosphere likely created a stable climate that maintained the pressure and temperature necessary for liquid water. But over billions of years, Mars lost most of its atmosphere, leading to the arid conditions we see today. One of the main theories about the loss of Mars' atmosphere is the effect of the solar wind. The solar wind is a stream of charged particles coming from the sun. Unlike Earth, Mars does not have a global magnetic field to protect its atmosphere. The Earth's magnetic field acts as a shield that deflects the solar wind and keeps our atmosphere in place. Mars, however, lacks this protection, so the solar wind interacts directly with the Martian atmosphere, gradually stripping it away. This process, called atmospheric sputtering, occurs when solar wind particles collide with molecules in the atmosphere of Mars and launch them into space. As the Martian atmosphere thins, its ability to retain heat decreases, and the drop in atmospheric pressure and temperature cause the remaining liquid water to freeze or sublimate. Sublimation is when a solid turns directly into gas, skipping the liquid phase. This process likely contributed to the loss of surface water from Mars, as the low pressure and temperature made it impossible for liquid water to remain. The weak gravity of Mars has played an important role in the loss of its atmosphere and water. With only about 38% of the Earth's gravity, Mars cannot retain the gases in its atmosphere as effectively as the Earth. Over time, lighter molecules, such as hydrogen and oxygen, essential for water, gradually escaped into space. This continuous loss of gases further depleted the atmosphere of Mars, worsening the planet's ability to retain water. In the past, volcanic activity on Mars was much more intense. At the beginning, the planet experienced large volcanic eruptions that released gases into the atmosphere. These gases helped maintain a greenhouse effect that kept Mars warm enough for liquid water to exist. However, as volcanic activity decreased, the atmosphere stopped replenishing, leading to its thinning and, eventually, the cooling and desiccation of the planet. Although much of the atmosphere and surface water of Mars has disappeared, significant amounts of water still exist in the form of ice. Recent discoveries by rovers and orbiters have revealed vast deposits of water ice just below the surface, especially in the polar regions. Radar data from missions, such as the Mars Reconnaissance Orbiter, has detected large underground ice sheets that could contain more water than all of Earth's Great Lakes combined. Some scientists also believe that liquid water may exist in underground lakes protected by layers of ice and earth. These hidden water sources provide clues about the wet past of Mars and hold potential for future exploration. The state of the iron core of Mars has also shaped the history and current conditions of the planet. Unlike Earth, which has a molten iron core that generates a strong magnetic field, the iron core of Mars is mostly solidified, resulting in a weak magnetic field. Without a strong magnetic field, Mars became vulnerable to the solar wind, a stream of charged particles coming from the sun. For billions of years, these particles stripped away the atmosphere of Mars, leading to the loss of water on the surface. This weakened magnetic field not only led to atmospheric loss, but also affected the ability of Mars to maintain a stable climate. Understanding what happened to the water on Mars is key to future human exploration. Water is essential for life and will be vital for astronauts on Mars, as it can be used for drinking, growing food, and producing fuel. Learning to locate and extract water from the Martian subsurface will be crucial for long-term human missions to the Red Planet. Mars serves as a valuable laboratory for studying how planetary atmospheres evolve and the factors that affect their stability. By comparing Mars to Earth and other planets, scientists can create better models to predict changes in Earth's climate and explore the potential for life elsewhere. Recent missions, such as NASA's Perseverance rover and the European Space Agency's ExoMars mission, focus on the search for signs of past life on Mars. These missions study the geology of the planet and look for biosignatures, chemical or physical markers that could indicate past or present life. Water is fundamental to these investigations, as it is essential for life. By understanding where water existed on Mars and how it interacted with the planet's geology, scientists can better assess the potential for ancient life on Mars. The history of water on Mars is one of planetary changes and the dynamic processes that shaped the solar system. Although many unanswered questions remain, each new discovery brings us closer to understanding this mysterious planet. The history of water, the atmosphere, and the climatic evolution of Mars continues to inspire both scientists and explorers, driving the search for answers on our neighboring world. This modern image of Mars, taken from a spacecraft, shows evidence of ancient rivers, revealing that Mars was once a world capable of harboring life about 3 billion years ago. Far from being just a symbol of war or fear, Mars represents an opportunity and hope for future expansion. One of the most iconic and enduring features of our solar system is Jupiter's Great Red Spot. This enormous storm, larger than Earth itself, has been raging on Jupiter for at least 400 years and possibly longer. The Great Red Spot is a gigantic swirling storm that has fascinated astronomers and scientists since it was first observed. But what exactly is the Great Red Spot and why has it lasted so long? Let's explore the details to discover the secrets of this colossal storm. The Great Red Spot is essentially a high-pressure region in Jupiter's atmosphere that produces an anticyclonic storm, meaning it rotates counterclockwise in the planet's southern hemisphere. This storm is so large that it can be easily seen through telescopes from Earth. In fact, it is approximately 13 times the diameter of our planet, with its edges rotating faster than its center. One of the most striking features of the Great Red Spot is its distinct reddish color. The scientists are still not entirely sure what causes this vibrant hue. Some theories suggest that the red color comes from chemical substances in the atmosphere of Jupiter, such as phosphorus, sulfur, or organic compounds that could be altered by the ultraviolet light of the sun. Ultraviolet light of the sun. Another idea is that the color could come from deeper layers of the storm itself, with different chemical substances that are stirred from below. Regardless of its origin, the red color makes the Great Red Spot stand out against the white, brown, and yellow bands of Jupiter's turbulent atmosphere. One of the great mysteries surrounding the Great Red Spot is its remarkable longevity. On Earth, storms usually last only a few days or weeks. However, the Great Red Spot has persisted for centuries. This durability is largely due to Jupiter's unique atmospheric conditions. Jupiter is a gas giant, which means that it does not have a solid surface like Earth, but is mainly composed of hydrogen and helium with traces of other gases. This lack of solid surface allows storms to last much longer, as there is no land to interrupt them. In addition, Jupiter's immense size and rapid rotation contribute to the stability and longevity of the Great Red Spot. Jupiter's rapid rotation is crucial to maintaining the Great Red Spot. The planet completes a rotation in just under 10 hours, much faster than Earth's 24-hour day. This rapid spin creates strong jet streams that help maintain and contain the storm. These jet streams act as barriers that keep the Great Red Spot confined to its region, preventing it from dissipating. The interaction between these jet streams and the storm itself helps maintain its structure and intensity over time. Despite its impressive longevity, the Great Red Spot is slowly shrinking. Observations made over the last decade show that the storm has been gradually shrinking. When it was first measured in the late 19th century, the Great Red Spot was about 25,000 kilometers wide. Today, it is significantly smaller, although still larger than Earth. Scientists continue to monitor the storm to understand how long it will persist. In summary, the Great Red Spot of Jupiter is a giant storm unlike any other on Earth, with its size, color, and longevity captivating the imagination of astronomers for centuries. Although the storm is slowly shrinking, it remains one of the most fascinating features of our solar system and a reminder of the dynamic forces acting on gas giants like Jupiter. Today, the Great Red Spot is less than half the size it was in the late 19th century. Scientists are closely monitoring this contraction to understand why it is happening and what that could mean for the storm's future. The exact reasons for this gradual contraction remain unclear, but could be related to changes in the atmosphere of Jupiter or to interactions with other storms, and the dynamics within the Great Red Spot are complex. The storm's winds can reach speeds of up to 400 miles per hour, creating towering clouds that rise above the surrounding atmosphere. The storm also has a layered structure with different temperatures and wind speeds at various altitudes. The top of the Great Red Spot is much colder than the surrounding clouds, suggesting that the storm extends deep into Jupiter's atmosphere. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, has provided new insights into the Great Red Spot. Equipped with instruments designed to study Jupiter's atmosphere and internal structure, Juno has revealed that the storm extends much deeper into Jupiter's atmosphere than previously thought, possibly hundreds of miles. This depth indicates that the Great Red Spot is a towering storm rooted in the deep gaseous layers of the planet. The Great Red Spot not only helps scientists understand Jupiter, but also gives clues about the atmospheres of other planets, including exoplanets, worlds beyond our solar system. By studying this enormous storm, scientists can create models to predict weather patterns on other gas giants and potentially habitable planets. The knowledge gained from the Great Red Spot helps us understand how atmospheres behave in distant worlds. Despite centuries of observation, the Great Red Spot still captures our imagination. It reminds us of the immense and powerful forces that act in our solar system. Each new discovery about the storm brings us closer to understanding its mysteries, while highlighting how much remains to be learned about Jupiter and other giant planets. The Great Red Spot has also become a cultural icon, appearing in countless works of art and science fiction literature. It symbolizes the wonders of our solar system, and its appearance and lasting presence have made it a favorite of both professional and amateur astronomers. Observing the Great Red Spot through a telescope is an exciting experience that connects us to the vast universe beyond Earth. Studying the Great Red Spot also helps us appreciate Earth's atmosphere. Although storms on Earth are much smaller and shorter in duration, they still follow similar atmospheric principles. Understanding the dynamics of this enormous storm on Jupiter allows us to better understand how atmospheres work, even on our own planet. The future of the Great Red Spot is uncertain. Will it continue to shrink and eventually disappear, or could it stabilize and last for many more centuries? Scientists are eager to find out, and ongoing observations from missions like Juno will be key to answering these questions. The data collected will help scientists build more accurate models of Jupiter's atmosphere and understand the long-term behavior of its most famous storm. The sixth planet from the Sun is a world full of wonders. One of its most fascinating features is the unusual hexagonal storm that revolves around its North Pole. This geometric storm has captured the curiosity of scientists and space enthusiasts alike, as it presents a phenomenon unlike anything seen on Earth or any other planet in our solar system. First discovered by NASA's Voyager spacecraft during its flights in the early 1980s, Saturn's hexagonal storm is a massive and lasting weather pattern. Unlike the circular storms we know on Earth, this storm has a clear hexagonal shape. Each side of the hexagon is about 14,500 kilometers long, making it more than twice the diameter of Earth. The storm also contains a powerful jet stream with wind speeds reaching 320 kilometers per hour. What makes Saturn's hexagonal storm so remarkable is not only its size and shape, but also its persistence. The storm has lasted decades, showing few changes in its structure or position, while storms on Earth last only days or weeks. This hexagon has remained stable for at least 40 years, and possibly much longer. Scientists have proposed several theories to explain how Saturn's hexagonal storm forms and is maintained. One of the main ideas is that the hexagon is created by a pattern of standing waves in the atmosphere of Saturn over Earth. Standing waves can occur both in the oceans and the atmosphere, generating stable patterns that do not move with the flow of air or water. Similarly, the hexagonal section could be a standing wave created by the interaction of Saturn's atmosphere with its rapid rotation and internal heat. Saturn's atmosphere is mainly composed of hydrogen and helium, with small amounts of gases such as methane, ammonia, and water vapor. It rotates once every 10 hours, creating strong jet streams and turbulent weather patterns. These jet streams can interact in complex ways, and the standing wave theory suggests that these interactions form a hexagon that blocks the storm in its hexagonal shape. Another idea is that the hexagon is the result of the unique atmosphere of Saturn, which has different layers, each with its own temperature, pressure, and composition. The interactions between these layers can produce stable, geometric patterns. Laboratory experiments on Earth have shown that rotating fluids can form similar hexagonal shapes, supporting the idea that the hexagon is a natural result of Saturn's atmospheric dynamics. One of the most striking features of the hexagonal storm is its color. The NASA Cassini spacecraft, which orbited Saturn from 2004 to 2017, captured images showing the hexagon in blue and gold tones. The color differences are probably due to seasonal changes in Saturn's atmosphere. During the boreal winter, the hexagon appears blue, possibly due to the lack of sunlight and the condensation of certain gases. With the arrival of spring and summer, the hexagon acquires a more golden tone, probably because sunlight triggers the production of photochemical mist. During the first 5 years of the Cassini mission, it was impossible to see the hexagon in visible light because the North Pole was in winter darkness, which lasts about 7 years in Saturn. But in December 2009, with the arrival of spring, the sun began to shine again on the North Pole, which allowed Cassini to take the first detailed images of the hexagon of Saturn, revealing characteristics that had never been seen before. Researchers at the University of Oxford provided more information about the hexagon by simulating Saturn's atmosphere and the behavior of the rotating jet stream by adjusting the speed of the jet stream and the surrounding atmosphere in their models. They were able to recreate shapes, including a hexagon, that offer clues about how this strange storm forms and persists. Saturn's hexagonal storm remains one of the most fascinating meteorological patterns in our solar system, showing the complexity of planetary atmospheres and the unique forces acting on gas giants like Saturn. The hexagon of Saturn is formed by an intense jet stream that mixes with the surrounding atmosphere, and in its center, there is a huge rotating storm that has lasted for decades. In 2013 and 2017, NASA's Cassini spacecraft captured close-up images of the hexagon, which were combined to create 2 videos from those years. However, a new question arises. Why did the hexagon's color change during those 4 years? The Cassini mission provided detailed data on Saturn's hexagon, revealing many things that were previously unknown. For example, Cassini observed a huge hurricane-like storm in the center of the hexagon, with a clearly defined eye and rapidly moving winds. This central storm is surrounded by towering clouds that reach heights of up to 100 kilometers above the surrounding cloud tops. Cassini data also showed that the hexagon extends deep into Saturn's atmosphere, demonstrating that it is not just a surface feature, but a multi-layered structure. Understanding Saturn's hexagonal storm goes beyond discovering a planetary feature. It also helps us learn more about how atmospheres work. The study of this storm can provide information on how fluids and gases behave under extreme conditions, which could improve weather models of Earth and other planets. The hexagon also allows scientists to study the effects of rotation, convection, and wave interactions in planetary atmospheres. The stability of Saturn's hexagonal storm raises questions about how long weather systems can last on planets, how these patterns form, and what factors allow them to last so long. By examining the hexagon, scientists can better understand the processes that drive weather patterns on gas giants like Saturn and possibly other planets beyond our solar system. In recent years, scientists have used computer models to simulate the hexagon and test different ideas about its formation. These models have shown that rotating fluids can create stable hexagonal shapes under certain conditions. By adjusting the parameters of these models, researchers can explore how factors such as Saturn's rotation speed, atmospheric composition, and internal heat contribute to the formation and maintenance of the hexagon. Saturn's hexagonal storm remains an area of active research. Each discovery adds to our knowledge about this feature and the dynamic processes that shape planetary atmospheres. Future missions to Saturn and other gas giants are planned. Scientists hope to collect even more data to better understand the hexagon and other phenomena. In summary, Saturn's hexagonal storm is an extraordinary feature that challenges our understanding of planets and planetary climate. Its shape, enormous size, and long presence make it one of the most unique phenomena in our solar system. By studying the hexagon, scientists gain valuable insights into the dynamics of Saturn's atmosphere and the general principles that govern the behavior of fluids and atmospheric patterns. As we continue exploring our solar system, Saturn's hexagonal storm stands out as a symbol of the complexity and beauty of the universe. One of the biggest mysteries of space is whether we are really alone in the universe or even in our solar system. We have recently found indications that there could be life elsewhere, possibly on the moons of Jupiter and Saturn. Water is crucial for life as we know it. Astrobiologists who study the possibility of life beyond Earth say that other important ingredients include certain chemicals and a stable energy source over time. Earth was the only known world with liquid water, but we now know that at least two other places, Jupiter's moon Europa and Saturn's moon Enceladus, have global oceans beneath their icy surfaces. There are also indications that water may exist elsewhere. What about other ingredients for life? Europa and Enceladus could have those too. When the Cassini spacecraft discovered a plume of water vapor and icy particles on Saturn's moon, scientists were intrigued. Initially, Cassini was scheduled to fly over Enceladus only 3 times, but ended up making 23 passes, collecting more information about the moon's chemistry and vapor column each time. What do they find? A salty ocean under Enceladus, icy crust, and strong indications of hydrothermal sources. These sources, similar to those at the bottom of Earth's oceans, release chemical substances that support tiny shrimp and other creatures. Jupiter's moon, Europa, offers similar clues. Data from the Galileo mission suggests it also has a global ocean beneath its icy surface. Later, the NASA Hubble Space Telescope detected what could be columns of water vapor on Europa. To investigate further, NASA is developing Europa Clipper, a new spacecraft to study Europa in more detail. These moons could have environments similar to Earth's deep oceans, where life thrives around hydrothermal vents. On Earth, these vents support entire ecosystems, including shrimp, crabs, and microorganisms. These creatures do not depend on sunlight for energy, but use the vent's chemical energy demonstrating that life can survive in extreme conditions. Both Europa and Enceladus have thick ice layers floating on their oceans. Scientists believe that beneath these ice layers are warm, salty oceans that could harbor life. The ice acts as a shield, protecting the oceans from the harsh conditions of space, making these moons some of the most promising places to look for life beyond Earth. The discovery of plumes on Enceladus was a great advance. These plumes shoot out from cracks in the moon's icy layer, known as tiger stripes, and extend hundreds of kilometers into space. The Cassini spacecraft studied these columns, analyzing their composition and detecting water vapor, ice particles, and organic molecules. The presence of these organic molecules suggests Enceladus has the basic components for life. Cassini's findings also showed that the columns contain salts and other minerals that point to hydrothermal activity at the ocean bottom. On Earth, hydrothermal sources support diverse ecosystems fueled by chemical substances released from vents. If similar conditions exist on Enceladus, there is a possibility that life exists in its hidden ocean. NASA's Europa Clipper mission, scheduled to launch in October 2024, aims to explore Europa in greater detail. This spacecraft will carry instruments to study Europa's ice layer and subsurface ocean by flying close to Europa. The Europa Clipper will collect data on the moon's habitability, potentially detecting signs of water vapor plumes and studying conditions for life. Europa's surface is marked by a network of cracks and ridges that suggest its ice layer is active and possibly influenced by the ocean beneath. The Galileo mission also found evidence of a magnetic field around Europa that is believed to be generated by a salty, conductive ocean beneath the ice. This magnetic field supports the theory of an underground ocean. The potential for life on Europa and Enceladus goes beyond having liquid water and organic molecules. These moons also have energy sources that could sustain life, as on Earth. Life thrives in extreme environments where energy comes from chemical reactions rather than sunlight. Hydrothermal sources on the ocean floors of Europa and Enceladus could provide the energy needed for life. In addition to the Europa Clipper, future missions are planned to explore these moons. One of them is the Enceladus Life Finder, which aims to analyze Enceladus columns in more detail by studying their composition. Scientists hope to detect signs of life or the conditions that could sustain it. The search for life on Europa and Enceladus is part of a broader effort to understand the potential for life elsewhere in the solar system. The age of the universe is one of the greatest scientific mysteries. The most accepted explanation about the origin of the universe is the Big Bang Theory. According to this theory, the universe began as an incredibly hot and dense point about 138 billion years ago. This tiny point contained all the matter and energy that would eventually become everything we see today. Since then, the universe has been expanding, cooling, and forming structures such as galaxies, stars, and planets. Scientists use various methods to determine the age of the universe, including studying the cosmic microwave background radiation, observing the rate of expansion of the universe, and analyzing the oldest known objects in the universe. One of the most important tests to determine the age of the universe is the CMB, discovered in 1965 by Arno Penzias and Robert Wilson. The CMB is residue of the Big Bang, the leftover heat from the early universe, now cooled and stretched in a microwave wavelengths due to the expansion of the universe. The European Space Agency's Planck satellite has provided the most accurate measurements of the CMB. Planck's data has helped scientists determine that the universe is approximately 138 billion years old. The CMB gives us a clear picture of the universe when it was only 380,000 years old. By studying small differences in the CMB, scientists can learn about the initial conditions and how it has changed over time. These variations tell us about the distribution of matter and energy in the early universe, which helps us estimate its age. Another method to determine the age of the universe is observing its expansion. In the 1920s, the astronomer Edwin Hubble discovered that galaxies move away from us. The farther a galaxy is, the faster it seems to move. This relationship is known as Hubble's law. Measuring the Hubble constant allows scientists to estimate the time elapsed since the Big Bang, giving us an estimate of the age of the universe. The Hubble constant measures the rate at which the universe expands. Determining the Hubble constant allows scientists to estimate how long the universe has expanded since the Big Bang. For this, measure the redshift of distant galaxies and calculate their distances using methods such as observation of variable stars and supernovas. However, finding the exact value of the Hubble constant has been complicated, since the different ways of measuring it have given slightly different results, which has given rise to what is known as the Hubble tension. Despite this difference, the average value of the Hubble constant, combined with other data, supports the idea that the universe is about 138 billion years old. Over time, different methods, such as observation of Cepheid stars and the study of the CMB, have consistently supported the Big Bang theory and our estimate of the age of the universe. Stars also give us clues about the age of the universe. By studying the life cycles of stars, scientists can estimate the ages of the oldest star clusters. An important type of star for this purpose are globular clusters. White dwarf stars are the remains of stars that have exhausted their nuclear fuel. They also provide useful age estimates by analyzing the rate at which white dwarf stars and globular clusters cool. By studying the light of these stars and comparing it with models of stellar evolution, scientists can calculate how long these stars have been cooling and therefore how many years they have. Scientists can estimate the age of the clusters, since globular clusters formed shortly after the Big Bang. Their ages give us a lower limit for the age of the universe. The oldest globular clusters and white dwarf stars are around 13 billion years old. Since these objects must have formed after the Big Bang, their ages support the estimated 138 billion years for the age of the universe. Another method to find out the age of the universe involves the radioactive disintegration of certain elements, as uranium and thorium decompose at a predictable rate. Measuring the proportions of these elements in old stars and meteorites allows scientists to estimate how long has passed since these elements formed. This technique, called radioactive dating, has provided age estimates that match other methods, supporting the idea that the universe is about 138 billion years old. Gravitational waves, ripples in space-time caused by large cosmic events, offer another way to study the history of the universe. Detected for the first time in 2015 by the LIGO and Virgo observatories, gravitational waves provide a new way to measure the Hubble constant and estimate the age of the universe. By observing fusions of neutron stars and black holes, scientists can use gravitational waves to calculate distances and track the expansion rate of the universe. This new approach to gravitational wave cosmology promises even more accurate estimates of the age of the universe. According to the theory of general relativity, our universe has certain characteristics. It is uniformly dense on a large scale, it has consistent laws and properties, and the Big Bang occurred everywhere at once. These characteristics connect the age of the universe with its expansion history. To determine this, scientists rely on various observations. These observations include direct measurements of the brightness and distance of celestial objects, helping us build the cosmic distance ladder. They also include studies of large-scale structures, clusters of galaxies, and baryonic acoustic oscillations, as well as fluctuations in the cosmic microwave background, giving us a snapshot of the universe when it was only 380,000 years old. In summary, scientists use multiple methods to determine the age of the universe, including the study of the cosmic microwave background, the observation of the redshifts of distant galaxies, the analysis of the life cycles of stars and globular clusters, and the exploration of the effects of dark matter and dark energy. Each method provides valuable information, and, together, they give us a clearer picture of the age of the universe and how it has evolved. Another practical approach that scientists use to determine the age of the universe is the study of the brightness and distances of certain stars known as standard candles. One of the most famous examples is the use of Cepheid variable stars. These stars have a known relationship between their brightness and the period of their variations. By measuring the period of these variations, scientists can determine the actual brightness of the star and, by comparing it with its observed brightness, calculate its distance from Earth. This helps to build what is called the cosmic distance ladder, a fundamental tool for estimating the age of the universe. In addition to stars, scientists use supernovas as another type of standard candle. These supernovas occur in binary star systems, in which one of the stars is a white dwarf. When the white dwarf reaches a certain mass, it explodes with a predictable brightness. By observing these explosions in distant galaxies, astronomers can determine the distance to these galaxies and, together with their redshift, estimate the expansion rate of a universe. Another practical method is radioactive dating, particularly in old meteorites. Elements such as uranium and thorium decompose over time at well-known rates. By measuring the proportions of these elements in meteorites, scientists can estimate how long has passed since these elements formed, providing a lower limit for the age of the universe. These practical techniques, combined with observations of the cosmic microwave background and the study of the redshifts of galaxies, come together to provide a consistent estimate that the universe is about 138 billion years old. A consistent estimation is of around. In 1950, the famous physicist Enrico Fermi asked a simple but important question during lunch with his colleagues. If our galaxy is so big, where are all the advanced alien civilizations? This question is now known as the Fermi paradox. The paradox comes from the fact that, with around 400 billion stars in our galaxy, it seems likely that some planets harbor intelligent life. If that is true, these civilizations would have had plenty of time to explore and perhaps even visit Earth, but we have not yet found any clear evidence that this has happened. To explain why we have not seen any sign of extraterrestrial civilizations despite the high probability that they exist, several theories have been proposed. One theory is that traveling between solar systems can be extremely expensive and require vast resources. For example, sending a spacecraft even to the nearest star would require an enormous amount of energy and money, making it impractical. Another theory suggests limited expansion. Even if a civilization starts exploring and colonizing other planets, it could be difficult to continue expanding across generations. The effort needed to travel from one stellar system to another could be too difficult to maintain. Some ideas suggest that the galaxy could be full of activity, but we are in a quiet part where not much happens. Others suggest that Earth could be like a zoo or a nature reserve where aliens observe us from a distance to ensure we don't know they exist. To understand the Fermi paradox, we must consider two key ideas. The first is the Drake equation, created by Frank Drake, an important figure in the search for extraterrestrial life. This equation suggests that there could be thousands of civilizations in our galaxy capable of sending signals to us. The second is the Fermi paradox itself, which asks why we have not found any clear signal of intelligent extraterrestrials, such as evidence of interstellar travel. Despite its name, the Fermi paradox was not created by Enrico Fermi, but it has become an important idea when debating the possibility of extraterrestrial life and has influenced research in this field. The name Fermi paradox is a bit misleading since, although it is named after physicist Enrico Fermi, he was not the one who created this idea. However, it has become an important concept when debating the possibility of extraterrestrial life and has influenced research funding decisions. Interestingly, the term Fermi paradox does not originate from Fermi himself. What we know of his thoughts comes from a lunch in Los Alamos in 1950, as remembered by physicist Eric Jones, who interviewed Fermi's colleagues, Emil Kopinski, Edward Teller, and Herbert York. During this lunch, Fermi was curious about space travel and wondered why, if the universe was so vast, there was no clear evidence of extraterrestrial visitors. According to Teller and York, Fermi was primarily interested in the feasibility of interstellar travel, not necessarily in the existence of extraterrestrials. Such skepticism made sense at that time, since space travel was still in its infancy. The modern interpretation of the Fermi paradox, which questions the absence of evidence of extraterrestrial life despite the high probability of its existence, was not fully formulated by Fermi. In fact, The idea that the absence of aliens on Earth implies their absence throughout the galaxy was first proposed by astronomer Michael Hart in 1975. Hart argued that if intelligent aliens existed, they should have already colonized the Milky Way, since we have not seen any evidence of them on Earth. He suggested that humanity could be the only intelligent civilization in our galaxy. He even thought that searching for alien civilizations could be a waste of time and resources. However, many people disagree with his conclusion and offer several counterarguments. Some suggest that interstellar space travel could be too difficult, even for advanced civilizations. Others argue that an advanced civilization may have no interest in colonizing other planets, or that they may have visited Earth long before humans existed, leaving no visible traces. In 1980, physicist Frank Tipler expanded Hart's ideas by considering the enormous resources needed to explore billions of stars. Tipler introduced the idea of self-replicating robots with human intelligence. These robots could in theory be sent to nearby stars, where they would use local resources to create copies of themselves and continue spreading throughout the galaxy. Tipler concluded that since we have not found any evidence of these advanced robots on Earth, this could suggest that we're the only intelligent civilization not only in the Milky Way, but in the entire universe. This bold idea is based solely on the absence of evidence, which remains a highly debated topic in the search for extraterrestrial life. What we now call Hart's paradox comes mostly from the ideas of Michael Hart and Frank Tipler, but over time their theories have been combined with Enrico Fermi's original question, creating some confusion about the real origin of the paradox. This confusion probably started in 1977, when physicist David Stevenson used the term Fermi paradox in a publication in which he presented Hart's theory as an answer to Fermi's question. A more accurate name for this concept could be Hart's level argument against the existence of technological extraterrestrials. Although this name is not as catchy, it would better recognize the true creators of the idea. Despite the confusion, the search for extraterrestrial life remains an important scientific focus. New tools such as the James Webb Space Telescope are providing impressive images and data, while rovers on Mars continue to study the planet closely. There are also plans to explore the farthest parts of our solar system, as the question of whether we are alone in the universe remains unanswered. An important area of research in the search for extraterrestrial life involves the study of exoplanets, planets that orbit stars outside our solar system. The Kepler Space Telescope and other missions have discovered thousands of exoplanets, some of which are in the habitable zone, the region around a star where conditions could allow liquid water, a key ingredient for life as we know it. Life also requires certain elements, such as carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements, the basic components of organic molecules, are common throughout the universe and have been found in interstellar clouds, comets, and even on other planets and moons in our solar system. Scientists look for biosignatures, that is, signs of life that can be detected remotely. These could include specific gases in a planet's atmosphere, such as oxygen or methane, which could indicate vital processes. Another area of research is the search for technosignatures, that is, signs of advanced civilizations. This includes the search for radio signals, laser pulses, or other technological markers that may suggest intelligent life projects. Projects like SETI have been scanning the skies for decades in the hope of detecting signals from alien civilizations. Closer to home, researchers are exploring the possibility of life within our own solar system. Moons like Europa and Enceladus, which have underground oceans under their icy surfaces, are of special interest. These oceans could have the right conditions for life, protected from space by thick layers of ice. As technology continues advancing, our capacity to look for extraterrestrial life will keep improving. New telescopes, space missions, and artificial intelligence tools will improve our ability to detect and study possible signs of life, bringing us closer to answering one of the great questions: are we alone in the universe?